What if the darkest objects in the universe are also some of the best teachers we have? A black hole is not a cosmic vacuum cleaner. It is a region where gravity has become so intense that beyond a boundary called the event horizon, light can no longer escape. That boundary is not a solid surface. It is more like a point of no return. If you stay outside it, a black hole can orbit and behave gravitationally like any other object with the same mass. If the sun could somehow become a black hole with the same mass Earth would not be sucked in. It would keep orbiting. The problem is that real black holes form from extreme events, usually when massive stars collapse or when dense objects grow over cosmic time. Black holes matter because they reveal gravity at its most intense. Around them, gas can heat to enormous temperatures. Stars can whip around invisible centers. Galaxies can be shaped by supermassive black holes, millions or billions of times the sun's mass. What is known is powerful. We have measured stars orbiting the black hole at the center of the Milky Way. We have detected gravitational waves from black holes merging. We have even imaged the glowing material around distant black holes. What remains uncertain is just as fascinating. We do not fully understand what happens at the deepest center where our current physics strains. We also do not know every detail of how the biggest black holes grew so early in cosmic history. They force simple questions to become profound. What is space? What is time? What happens when matter is compressed beyond any ordinary scale? In that sense, they are cosmic tests. A black hole is not just an ending. It is a natural laboratory carved out of gravity itself. And to understand why they hold our attention, we have to look at the strange way they bend both space and imagination. Black holes feel impossible because they turn emptiness into something active. Most space objects shine by sending light toward us. A black hole is different. We learn about it by watching what it does to everything nearby. If gas falls toward one, it can flatten into a fast glowing disk. The gas is not glowing because the black hole is shining like a star. It is glowing because friction pressure and gravity are heating it before it crosses the point of no return. In some systems, powerful jets can blast outward from the region around the black hole, though the exact details depend on magnetic fields and matter swirling close to the edge. This is part of the pull. Black holes are invisible, but not silent. They tug on stars. They distort light. When two merge, they shake space-time itself, sending gravitational waves across the universe. Those waves are not sound in space. They are tiny stretches and squeezes in distance, detected by extremely sensitive instruments on Earth. The fascination also comes from contrast. A black hole can be born from the death of a massive star, yet supermassive black holes sit in the hearts of galaxies. Some are a few times the mass of the sun. Others outweigh the sun by millions or billions. The same basic idea appears on wildly different scales. What scientists know is that black holes are real astrophysical objects, not just equations. Their effects have been observed in multiple independent ways. What scientists are still testing is how black holes grow, how jets launch, and how gravity behaves, where conditions become extreme. They attract attention because they sit at the edge of the visible universe. We cannot see the hole itself. We see the universe reacting to its presence, and that reaction leads to the deepest question of all. What do black holes tell us about the limits of knowledge? The safest truth about black holes is also the most humbling. We know they are real, but not everything about them is understood. The evidence is strong. In our own galaxy, stars race around an unseen massive object called Sagittarius. A star, their orbits reveal a compact mass, millions of times heavier than the sun. The best explanation is a supermassive black hole. Far beyond the Milky Way, observatories have tracked energetic regions where matter heats up before falling inward. Gravitational wave detectors have recorded the mergers of black holes, letting scientists hear, in a scientific sense, the rhythm of space-time changing. Radio telescope networks have also produced images of glowing material around black holes, including the one at the center of the galaxy M87 and Sagittarius A star. So the basic picture is not guesswork. Black holes are part of modern astronomy, but the mystery begins where direct observation ends. The event horizon hides whatever passes inside. No signal from within can return to tell the outside universe what happened. General relativity describes the horizon and the gravity around it extremely well, but at the central singularity, predicted by the mathematics, the theory points toward conditions where a deeper theory is needed. That does not mean anything is possible. It means scientists are careful. Ideas about quantum gravity information and the internal structure of black holes are active research, not settled answers. There are also practical questions. How did the earliest giant black holes grow so quickly? How do some black holes launch jets across vast distances? How do black holes and galaxies influence each other over billions of years? The memorable takeaway is simple. Black holes are not holes in knowledge. They are places where knowledge is being tested. They mark a boundary in space and also a boundary in understanding. And beyond that boundary, the universe is still asking questions.